In order to ensure that this film and projector are adjusted for optimum viewing and listening, this motion picture comes to you with a focus and sound test leader. Please focus the picture and set the sound level at this time. When the picture fades out, the start of the film will follow shortly.
In an ancient time, a Greek engineer said that given a place to stand and to rest a lever, he could move the earth. And this was true. For man lives in a Euclidean world where the motion of any mechanical element with respect to another must follow a specific geometric pattern. Consequently, whatever science conceives, it can rarely be applied without the creative talent of the mechanical engineer. Put it in terms of examples. The task: design a shock testing device which will first heat a specimen to more than 1,000 degrees and then subject the heated specimen to 1,500 Gs. The task: provide a vacuum floating zone refiner which will operate at a pressure of 10 to the minus 10 torr and a temperature of 2,500 degrees centigrade. Task: design a heavily shielded cell in which transuranium elements may be manipulated and chemically processed using materials which must operate for long periods in kilocurie levels of alpha, beta, and gamma radiation and in the presence of corrosive chemical reagents. The task: develop a technique for cold welding metals, and in the process, develop a metal sealed vacuum system which will produce a pressure of 10 to the minus 12 torr using high temperature bakeable valves in close proximity to cryogenic liquids. The task: create laboratory simulation of nuclear phenomena by using a rapid deposition of luminous electromagnetic energy from a Q-switched ruby laser onto a target surface to propagate stress waves of extremely short duration. The task: work at the threshold of knowledge in a field that challenges every element of the mechanical engineer's training and experience, because this field in itself is pushing beyond the threshold in every known area of science. The field: nuclear energy, a force to move the earth. It is not generally recognized that the mechanical engineer is one of the most important figures in nuclear research, for while nuclear energy has the force to move the earth, it is the mechanical engineer who builds the lever. For this reason, at one of the foremost laboratories in the world devoted to nuclear research, the Livermore site of the University of California's Lawrence Radiation Laboratory, the importance of the mechanical engineer was recognized from the first. Because the demands of the field exceed the capabilities of any single science, it was in nuclear research that Ernest O. Lawrence, famed Nobel laureate, created and brought to its highest level the team concept of problem solving.
I'd be interested, I have to have the best material to get the maximum pressure. Now you can see how the thickness of the material affects the acceleration time for each of the separate accelerations. The thing that we don't know is the breakup. And we have to...
A key member of the scientific team is the mechanical engineer. And why not? Abstract theory must be translated into mechanical reality. And because in this field there are still few precedents to draw upon, creative freedom is a prime and necessary ingredient. The rule when working with nuclear projects is to give each team member his share of the problem, then allow him to solve it in his own way. Total involvement from beginning to end. And to solve his problem, the engineer must draw upon every element of his profession. Consider, for instance, the materials and environmental challenges involved in just one aspect of the nuclear energy field, the development of experimental apparatus for the testing of theories in nuclear physics. To help define experiment parameters of the task, the Livermore Laboratory has one of the largest computer facilities in the world. One of the latest developments in computer-aided design facilities is a unique time-sharing system comprised of over 200 remote stations located throughout the laboratory. With this online access to the computer center, there is a minimum need for special programming ability, although professional programmers are available if needed. This man-computer partnership represents the wave of the future for engineers. For example, on a display monitor, he can run virtually any type of analysis with instant results, not only calculations, but furnishing properties of materials, loads, shape geometries, converting units, and other criteria that will permit ready comparison between theory and test. More advanced computer graphic techniques make possible the visualization of dynamic phenomena, as well as multidimensional mathematical models. When drawings of complex configurations are required, digital plotting techniques may be applied by means of computer-driven automatic drafting machines. There are also skilled designers and draftsmen to help translate creative concepts into final detailed drawings. If he wishes, the engineer may work in the development of his own design, although here again, the demands of the field have made it essential to have a skilled staff of craftsmen and technicians. Plus an array of equipment whose applications are extremely unique, such as this creep test laboratory. But then, most industries do not normally require measurements to fractions of a light band. Or reactions in the microsecond range. The metrology laboratory at Livermore is meeting the demand for progressively tighter tolerances in nuclear assemblies through the development of sophisticated measuring techniques. These techniques are being applied not only to the part being fabricated, but to the manufacturing tool as well. By first measuring accurately the sources of machine error and their relative magnitude, then making various refinements, more accurate final geometries and surfaces can be obtained than previously achieved by hand finishing. One of the greatest challenges in the field of nuclear research is that of materials selection. Working with exotic materials is the norm. Complex parts have been precision machined from hafnium, rhenium, beryllium, germanium, silicon, lithium fluoride, carbon, and every form of plastic. Triaxial properties of rock materials are being studied at pressures up to 3 million psi in a unique high-pressure laboratory to understand better the forces generated by a nuclear explosion. At the Atomic Energy Commission's Nevada test site, the performance of materials in a high-flux radiation field is being investigated by means of a prompt burst reactor called Super Kukla. The reactor was engineered to subject various specimens to a microsecond pulse of intense radiation, simulating the radiation burst which would occur during a nuclear explosion.
Attention, reactor area. Inserting burst rods at burst speed in test mode.
Nevada also may be the site for underground testing of the experimental nuclear device. In addition to engineering the test device, mechanical engineers are involved in every aspect of the nuclear test program, including the design and development of nuclear containment equipment, such as these huge millisecond reacting gate valves. The engineering and installation of highly sophisticated diagnostic systems, most of which must respond to signals of microsecond duration. Then, after weeks and months of following every nuance of development, the engineer realizes the fruition of his ideas.
This is control. In 1 minute, the time will be minus 10 minutes. Area 2. "30 seconds to zero time. 25 seconds. 20 seconds. 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, zero time.
Simple experiments that we can do is accelerating plates like this into these two materials and measuring the stress through the two.
With the physics theory proven by means of the experimental device, work may now proceed with converting the knowledge gained into practical application for use in strategic and tactical weapon systems for national defense. These programs present unique challenges to the mechanical engineer, since military applications demand extreme performance reliability under severe environmental and operation conditions. For example, materials that had presented problems to the device engineer, primarily in terms of strength and nuclear absorption, now must also be considered in terms of weight and size, long storage life, and adaptability to production techniques. Because the operational environment of a nuclear weapon involves extreme static and dynamic forces, the engineer has available a complete environmental test laboratory. Test equipment includes vibration exciters that apply sinusoidal and random accelerations with a total force capability of 28,000 pounds into test specimens weighing up to 2,000 pounds. An 18-inch diameter horizontal pneumatically actuated shock tester with a maximum capability of 40,000 pounds of force. And several impact machines, such as this one, which is capable of producing a half-sine shock signature of 10,000 Gs for 300 microseconds. Determining the fracture characteristics of materials and structures composed of certain materials by non-destructive methods has always been a problem for the engineer.
Are we loading yet? No, it hasn't picked up load yet.
A system is being developed to conduct measurements by acoustic emission. This technique is used to study sonic and ultrasonic elastic waves which are emitted as a solid material is deformed.
Let's do 10,000 psi stress.
Picking up nicely.
30,000 psi stress.
Information obtained in this research study will be useful in making more accurate fracture predictions in complex load-bearing shapes.
Okay, we're starting to get close to failure now.
100,000 microstrips.
Okay, we're getting close. There she goes. It broke.
When existing equipment cannot produce the desired results, as often happens when working in the field of nuclear energy, the engineer must generate his own test mechanism. Here again, ingenuity and flexibility are necessary requirements for the mechanical engineer. Non-destructive testing follows the same pattern. For example, when existing radiography equipment would not produce clear, full penetrative pictures of dense materials in the field, a transportable 13 MeV linear accelerator was engineered and constructed. The system can produce sharp pictures through 10 to 13 inches of solid steel. But while the development of nuclear weapons has contributed to the defense of the nation and the free world, the knowledge gained has also found ready application in other areas. In New Mexico, a project called Gas Buggy employed a deeply buried nuclear explosion to stimulate the release of natural gas from reserves which could not be economically claimed by conventional methods. This overall research program, called Plowshare, is designed to explore the use of nuclear explosive energy for industrial applications. Success of this one experiment could make available vast new recoverable reserves of natural resources, not only of gas, but of oil and minerals. In addition to nuclear stimulation of natural resources, Plowshare is studying the use of nuclear explosives for large-scale excavation and earth-moving operations. This crater in Nevada, for example, was produced by a 100-kiloton thermonuclear explosion, the equivalent energy of 200 million pounds of high explosive. Well-placed harbors produced by this powerful force could generate great economic development for nations with extensive but inaccessible natural resources. In addition, multiple emplacement road charge techniques are being explored, such as this test in Nevada, to study the feasibility of cutting through mountains for railroads or highways. But most promising is the challenge to build a sea-level canal across the Central American Isthmus, a dream of mankind since Balboa first observed the Pacific Ocean. This forging ahead with practical plowshare projects is absorbing the talents of many engineers and scientists, because every undertaking must be engineered to fit the needs of each unique application. The problems these teams face in projects scattered over the globe are among the most challenging on Earth. Although the engineering teams working to harness the energy of the sun might argue the point. It has been estimated that if the thermonuclear energy could be extracted from the deuterium in the oceans of the world, it would fulfill all man's requirements for millions of years. Engineers working on Project Sherwood are extending the limits of their knowledge in an attempt to produce controlled thermonuclear reactions through the use of magnetically contained hot plasmas, whose temperatures reach 100 million degrees centigrade. At Livermore, several major research facilities are being used to investigate thermonuclear fusion. The Astron facility, for instance, required the development of an 1100 Gauss direct current field to shape a magnetic bottle inside a 90-foot-long high-vacuum chamber. The Astron linear induction accelerator, which injects electrons into the magnetic bottle, produces 4 MeV 1,000 ampere pulses at the rate of 1,400 pulses per second. The ALICE facility, ALICE standing for Adiabatic Low Energy Injection and Containment Experiment, is a mechanical engineer's dream, or nightmare. For example, constraining the 500,000-pound separation force of the unique cryogenically cooled magnet coil was something of an engineering challenge. Then, too, in order to perform plasma experiments, ALICE requires a chamber vacuum approaching that of outer space. To meet these requirements, many unique vacuum pumping methods are employed. One such method uses metal surfaces cooled to a temperature of 1.5 degrees above absolute zero by supercooled liquid helium to achieve a pressure of 5 times 10 to the minus 10 torr. The challenges facing engineers working on the nearby 2X controlled fusion facility would appear more massive in character. 2X employs a unique multiple magnetic compression principle in a large vacuum chamber to achieve the required plasma densities and temperatures. But while the engineering problems are considered among the most formidable in all science, the eventual control of thermonuclear fusion will generate unlimited electric power, thus paving the way to a new era for mankind. Much of the technology going into nuclear research programs grew out of experimental work conducted on Livermore's family of particle accelerators, such as the 500 keV LINAC. The increasing use of high-energy linear accelerators for particle physics research presents unusual problems to the engineer. Efficient use of these machines requires knowledge in such fields as beam optics, magnet design, and radiation absorption and shielding. At the moment, the big challenge is development of apparatus for the new 100 MeV traveling wave linear accelerator. Work with accelerators can lead the mechanical engineer into other interesting fields, such as electrical superconductivity. The phenomenon is being put to use in a high-altitude cosmic ray experiment in which a balloon will carry this 10 kilogauss saddle-shaped magnet into the stratosphere. At this altitude, primary cosmic rays having energies as high as 1,000 billion electron volts will be deflected and measured as they pass through the magnet's field. Elaborate superthermal insulation is required to maintain the superconducting material at a temperature of 460 degrees below 0 Fahrenheit. It was essential to make the magnetic coil superconducting, for the weight requirement for conventional electrical power equipment was intolerable. Another good example of the increasing demands being made on mechanical engineering is the growing biomedical program. These studies, in association with nuclear research, involve a unique blend of scientific skills. Designing equipment for the non-destructive counting of radiation absorption in biological specimens alone required a high degree of coordination in at least 5 science and engineering fields. One of the interesting features of these and the many other projects underway at the Livermore Laboratory is the degree of ingenuity required of the team engineers. Each of these projects is a one-of-a-kind creation, with each component designed to order. And because the nuclear field requires such a cross-pollination of talents, engineers must work closely with physicists, mathematicians, electronic engineers, chemists, and other specialists, as well as other mechanical engineers. For this reason, the engineer must keep informed of continuing developments, not only in his own field, but in all related fields as well. And since in nuclear research, engineers are often involved in pioneering projects, the publishing of technical papers is a fundamental part of any project. It is evident, then, that to the mechanical engineer, the field of nuclear research promises more than just a technological challenge. It also promises great opportunity, both now and in the foreseeable future. Here, progress is limited only by the engineer himself, his initiative, and his imagination. And in this age, when mankind has within his control a force to move the earth, he must have an abundance of both to meet the challenge of being a mechanical engineer.